Hello guys, welcome back to another video. Okay, so sorry about the long wait. I just lost the motivation to do more of these videos because in my tutoring center, my tutoring job, I've been getting more high school level assignments, and because of that, I really didn't feel the need to do high school level problems, even though these aren't really high school level problems, aren't they? Or are they? I don't know. But basically, I just got busier and I just didn't really feel the need to do more of these, really. But one day I just woke up and wanted to at least progress on these things because it's fun. Okay, so we're still going to do one or two integrals for each video, so it's going to be very slow, and I don't even know when the next video is going to be. By the way, there'll be two integrals that I'm going to be solving in this video to make up for all the time, for all the days I didn't post a video. Yeah, okay. So as usual, we've got this problem. So at first glance, I'm thinking there's nothing special about the integral. The integrand is just a polynomial of degree 5, which, while tedious to integrate, is still an easy integral by, let's say, calculus 1 standards in university. However, remember that this is the MIT integration B. You only have 20 minutes to solve 20 qualified questions, and you better take a very short amount of time to solve one of these. So you can try doing this using standard calculus 1 methods, like you can integrate this as integral of sorry, you can simply integrate this as 1 over 6x to the power of 6 plus x to the power of 5 plus 10 over 4 x to the power of 4 plus all the way, and then take the integration bounds to be negative 3 over 2 to negative 1 half, and then just proceed as usual. But that will take quite a long time. Not only that, it is prone to mistakes because you'll be inputting these fractions into these exponents when you substitute for x. So now, how do you actually solve this problem quickly? Well, there's a trick that you can use. That is by recognizing this as some kind of a form that involves uh, binomials. So here's the trick. This trick kind of requires you to remember some binomial expansions to the fifth power. And if you don't remember it, you can use the Pascal's triangle to aid you in it. Oh, sorry. 1. All right. So how do you read the Pascal's triangle? So basically, the Pascal triangle has several interpretations. The one that is important for our problem right now here is what would happen if you raise x plus 1 to the power of something where the n is an integer. So, for instance, if I put x plus 1 to the power of 2 here, the result is x squared plus 2x plus 1. And notice this the coefficients here matches the third row of the Pascal's triangle. That is actually uh maybe it's better to just relabel them as like the zeroth, first, second rows. And then here, the third row or the fourth row, the third row is or are the coefficients of x plus 1 to the power of 3. And this is x cubed plus 3x squared plus 3x plus 1. Okay, so you can see how we're going to use this Pascal's triangle. So I'm going to move it aside here. There. Okay. And then I'm going to show you how to simplify this integral using the fifth row of the Pascal's triangle, the one that contains 1, 5, 10, 10, 5, and 1. So we're going to invoke that form first, and then we are going to readjust because the original expression obviously isn't identical to this row, but we simply have to subtract terms as necessary. So this. All right. So notice the discrepancies between the top integral and the bottom integral. So the coefficients of x to the power 5, x to the power 4, and x to the power 3 all match up, but we still need to subtract minus 2x squared here to match the coefficient of x squared in the integrand. And then same goes for 5x and 1. So we have to minus 4x and minus 1 to get the original integral back. So that means this part here is x to the power 5. Sorry, x plus 1 to the power 5. So our integral becomes x plus 1 to the power 5 minus, this is here, this is 2 times x squared minus 2x, oh, plus 2x plus 1, but with an adjustment. So notice that if we multiply this, it becomes negative 2. If you multiply 2 and 1 here, you get negative 2. But you have negative 1 here. So you have to add 1 to get the form back. And notice that this here is x plus 1 to the power of 2. So simplifying again, we get x plus 1 to the power of 5 minus 2x plus 1 to the power of 2 plus 1 dx. And this is much easier to work with. So this is just a bunch of hidden u substitutions, but they're quite simple, so I'm just going to skip over it. So this is 1/6 times x plus 1 to the power of 6 minus 2/3 x plus 1 to the power of 3 plus x, where the integration goes from negative 3 over 2 to negative 1 over 2. All right, so if we substitute these values, fear not, because as you can see, so minus 1/2 plus 1 is 1/2 to the power of 6 minus 2/3 minus 1 minus 1/2. This is 1/2. This is 1/2 power of 3 minus 1/2. And then 1/6 times minus 1/2 to the power of 6 minus 2/3 minus 1/2 to the power of 3 minus 3 over 2. So, okay, so let's take a look at this. Notice that these two terms are identical, so they cancel out. Wait, hold on. Yeah. Actually, I'm going to show you. So, let's see. Actually, these terms cancel out because negative 1/2 to the power of 6 is the same as equal to 1/2 to the power of 6. So these two terms cancel out. We have 2/3 1/2 cubed minus 1/2 plus 2/3 times negative 1/2 to the power of 3 plus 3 over 2. So this is minus 2/3 times 1 over 8 minus 1/2 plus 2/3 times -1/2, -1/8 plus 3/2. So you get -1/12 minus this is +1 because -1 plus 3/2 is +1. And then -1/12, which is 10/12 or 5/6. Right. And then the next integral that we're going to solve is this one. Right. So now we have a question from the 2024 quarterfinal where we have to integrate this function over 0 to 2 pi. Now, there are 3 layers of brackets here, and they all stand for different things. So let's take a look at each bracket, like what do they do, and try to unravel what it's actually asking. So you have 3 types of brackets, this, this, and straight brackets. So what is this? This bracket, this first type of bracket, which you can see surrounding the sine, cosine, tangent, cotangent functions, is the greatest integer function. Or function. So what does it actually do? It is it returns the integer that is lower than or equal to the number. So for instance, the floor function of let's say 1.3 here is 1. And then have the floor function of pi is equal to 3. So like because pi is 3.1415, etc. Uh, you just take the integer part because 3 is the largest integer that is equal to or greater than pi. Oh, sorry, the greatest integer that is lower than or equal to pi. And then for negative numbers like the floor function of negative 0.2, it will return 1. So the largest integer that is greater than, oh, sorry, the largest integer that is lower than negative 0.2 is -1. And if it's an integer, then it returns the integer itself. Okay. Now, what about the second bracket? The second type of bracket here is the set denominator. So basically what it's asking here is uh, what you have here is a set of numbers. The set of numbers that is defined as sine x, the set of numbers that are defined as the GIF, or I'm just going to, this is sometimes called the GIF. GIF of sine of x, cosine of x, tangent of x, cotangent of x. You will have up to 4 different numbers here, and then you put them into a set. So this is the set indicator. And then this here, what looks like this looks like an absolute value notation, but in the context of sets, it returns the number of elements in a set or the cardinality of a set. So for instance, if we have the set 1, 3, or 1, 2, 3, 4, then its cardinality is 4. If you have the set, let's say 2, 6, pi, then the cardinality is 3, because there are 3 different numbers. Okay, so you're thinking, how do you even simplify this? You've got a lot of seemingly unrelated brackets, and then somehow you're supposed to calculate this. Well, uh, before telling you to jump straight into the problem, I'm going to give you a bit of a I'm going to give you a bit of a walkthrough. So let's take a look at what happens when x is any particular value from 0 to 2 pi. By first thinking, what are the graphs of sine x, cosine x, tangent of x, and cotangent of x looks like? Okay, so this is the graph of sine of x. Okay, we've got some important numbers here. Pi over 2, pi, 3 pi over 2, and pi. And then the peaks here are 1 and -1. There you go. Okay, and then uh, if I take the GIF of sine of x, what does it do? It returns the integer, the largest integer that is lower than or equal to sine of x at any particular value of x. What would it look like? So if this is just sine x, then the graph of the GIF of sine x from 0 to 2 pi would look something like this. Uh, and then uh, there you go. And then the important points are pi over 2 pi. This is 3 pi over 2, and this is 2 pi. So this is -1, this is 1. Okay, how does the graph of sine of x get transformed into this graph on the right? So when x is any particular value, and we're going to start from 0 to 2 pi, from 0 to pi over 2, the value of sine x is less than 1. Well, the sine of the values of sine of x by itself lies between -1 and 1. And then at this interval, between this interval from 0 to 2 to pi over 2, the value of sine of x is between 0 and 1. If you take the GIF of any of those values, it is 0. So let's say the sine of x is 1/2. In the case where x is equal to pi over 6, then the GIF is 0. Same goes for square root of 2 over 2, it will be 0. Square root of 3 over 2, it will also be 0. So at any point from 0 to 2 pi over 2, the value of the GIF of sine of x is 0. And then there's a singular point here for x equals pi over 2. When x is equal to pi over 2, sine of x is 1. Sine of pi over 2 is 1. And the GIF is equal to 1. But notice that here there's only one point here because uh the value of sine of x is 1 at exactly 1 point, which is x equals pi over 2. And of course the other uh, of course, the other values because it's periodic, but we're only considering the values from 0 to 2 pi here. Okay, so, and then uh, from pi over 2 to pi, you will see that the value of sine of x decreases from 1 to 0. And for any value of sine of x, the GIF will be equal to 0. Then from pi to 3 pi over 2, notice that the value of sine of x becomes negative, and it lies between -1 and 0, meaning its GIF will be -1. At 3 pi over 2, uh, the same thing would happen to pi over 2. Sorry, the same thing would happen to the value of GIF of sine of x, but because the value of sine of x, where x is 3 pi over 2, is equal to -1, then this value is -1, the same as the surroundings. That's why there is no lone discontinuous point like in the case of x equals pi over 2. And then this behavior continues to 2 pi. Okay, so basically this is what it's asking. Now, you have to imagine what it's like for cosine, tangent, and cotangent. For cosine, it is quite similar. Actually, I ended up doing the question for you because, well, or maybe you can try to pause this video if you understand the gist of what we're doing here. So try to make these kinds of graphs for sine, cosine, tangent, and cotangent, and then see uh, how you do. For cosine of x, the graph looks like uh, this. Okay, it's a bit poor, but okay, so pardon my artistic skills. So 1, -1. This is pi over 2. This is pi. This is 3 pi over 2. This is 2 pi. Using the same principles, we can say that the graph of GIF of cosine of x is like this. Uh, so yeah, think about why the graph of cosine of x, sorry, the GIF of cosine of x looks like this by using the same principles as sine of x. There are some discontinuities that you will need to like resolve, as in where is the value for x equals pi over 2? Well, it will be here, not here. And then for this one, here too. This one is -1. Okay. Now, the graphs of tangent effects and cotangent effects might be a bit more difficult, and as well as the GIF functions. So here's the one for tangent. For tangent, you have asymptotes at x equals pi over 2 and x equals 3 pi over 2. So your graph looks like this. So this is pi over 2. Actually, I'm going to put it down. Pi over 2. This is pi. Pi over 2. This is 2 pi. Now, if we want to draw the value, sorry, the graph of the GIF of tangent of x, you will notice that once you hit x equals pi over 4, I'm going to put it here. So recall that tangent of pi over 4 is 1, and then tangent of 3 pi over 4 is equal to -1, and so on and so forth. So this is 1. This is also 1, so this here. And then you also have to need to worry about this. So this is 3 pi over 4. This here is 5 pi over 4. And this here is 7 pi over 4. Okay, I hope it's not too cluttered. Basically, why do we pick 1 as our point of interest? Well, between x equals 0 and pi over 4, the value of tangent of x is between 0 and 1. But after pi over 4 and up to pi over 2, the value of tangent of x goes from 1 to infinity. Now, we don't need to know the exact bounds for when tangent of x becomes 2, tangent of x becomes 3, and so on and so forth. All that matters is that once you hit x equals pi over 4, the GIF of tangent of x becomes a bit awkward, but we don't need to worry about it. So if I were to draw it, it looks something like this. So we have the asymptotes at the same locations, pi over 4. And then pi over 4, 3 pi over 2 here. Oh, sorry. Pi over 2 and 3 pi over 2. Okay. Then notice that when this is pi over 4, like here, the value of the GIF of tangent of x is 0 here. But then after that, this is 1. After that, it gives us some kind of a pattern that looks like this. So like these are red lines, which get shorter and shorter each time, which as you increase the value of x. Because the value of tangent of x simply grows without bound until x goes close and close to pi over 2. Like this. Now we don't need to worry about where tangent of x hits 2, 3, or 4, and etc. for a reason we'll see later. And then we should also draw the same thing for -1. So from -1, so from pi over 2 to 3 pi over 4, which should be, so this is pi here, and this here is 3 pi over 4. This is 5 pi over 4. It's a bit cluttered because it's like very small. What you will be looking at here is the graph would look like something like this. like that. And then from 3 pi over 4 to pi, you'll get this here from minus. So it stays -1 between 3 pi over 4 and pi. From pi to 5 pi over 4, it is 0. And then from 5 pi over 4 to 3 pi over 2, it exhibits the same behavior as you can see here. So like they're quite identical. And then don't forget the other the last interval here. So you have this here is 7 pi over 4, and then you have oh sorry. The shape of the graph would look like this. Wait, I am a bit. Oh, sorry. I will need to erase this. So that's 2 pi. So actually 7 pi over 4, 2, you've got this. And then before 7 pi over 4, the graph looks like this. Okay, right. Yeah, it's a bit cluttered. But you could say that the values of tangent of x, sorry, the GIF of tangent of x from pi over 4 to pi over 2 don't really have a pattern. Well, unless you happen to know the exact values of arctangent of 2, arctangent of 3, arctangent of 4, etc. So what about cotangent? For cotangent, let's draw an entirely different, let's use a different color. So for cotangent of x, this is equal to cosine x over sine of x, meaning it will not be defined when x is equal to 0. Sorry, sine of x is equal to 0. So it means your asymptotes are 0 and pi. So this is pi, and this is 0. And then what does the graph looks like? The graph looks like this. So this is pi over 2. And this here is also 2 pi. 2 pi is also another asymptote. This is pi over 2. This is 3 pi over 2. Right. Now, the same complications arise with cotangent of x. We also need to keep track of when cotangent of x hits 1 and -1. So that means here at pi over 4, and then so this here is, oh wait, so that's pi over 4, this is 1. And then here, it's -1. This here is 3 pi over 4. This here is 5 pi over 4. And this here is 7 pi over 4. if we translate that to the GIF function, what do you have? We have something like this. So this is, wait, hold on. Oh yeah, the asymptotes of pi n. Pi n 2 pi. Okay, so from x equals 0 to x equals pi over 4, the value of cotangent of x is decreasing from positive infinity to 1. So that means the graph looks like this. So this is pi over 4. The graph looks something like this until you get to 1, where the value of the GIF becomes 0, like this. And then from pi over 2 to 3 pi over 4, it becomes negative 1. So this is 3 pi over 4. And then from 3 pi over 4 to pi, it's chaotic again. So basically, this pattern repeats in the next cycle. So I'm going to leave it as an exercise for you to just verify that it goes from so you have different types of behaviors from pi to 5 pi over 4, and then 3 pi over 2, and then 7 pi over 4, and then from 7 pi over 4 to 2 pi. Okay. Right. So you might be able to draw this much clearer than I could. Now that we got this out of the way, let's try to solve it. Let's try to solve this integral. So as you can see, there are several important points for x where the value of the GIF could change. And then what we're doing here is that we're taking how many different values are there in all of these expressions. If there are the same values, if you see two expressions that yield the same values, you discard them because it's a set. You only need to have one copy of each member or each element of the set. So how many important points are there? Well, there are 8 at least. I mean, like you can define 0 to 2 pi into 8 different intervals. So 0 to pi over 4, then pi over 4 to pi over 2, pi over 2 to. So basically, uh, 1 over 4, 2 over 4, 3 over 4, 4 over 4, 5 over 4, 6 over 4, 7 over 4, and 8 over 4. So that's what exactly we're doing here. 3 over 4, 4 over 4, 5/4, 6/4, 7/4, and maybe hold on, this is actually 3/2. There. Right. Now let's see how many different values are there in the set. From 0 to pi/4, let's take a look at the values. So for pi/4, which is the midpoint between 0 and pi/2 here, the value of GIF of sine of x and cosine of x are 0, which means you only get one value. And then tangent of x also yields 0, but cotangent of x yields one of these values that goes from positive infinity to 1, which means you have two different values in that set. Because of that, the cardinality of this set will be 2 when x is between 0 and pi/4. So two different values. From pi/4 to pi/2, here, sine of x and cosine of x have GIF of 0. Tangent of x, on the other hand, have a chaotic value. I'm not saying chaotic. I mean, like, I'm saying is what I'm saying is basically like they might be unpredictable, but all of them will be different from 0, and the GIF of cotangent of x will be 0. So also two different values. Now, what about pi/2 and 3/4? This is where things start getting interesting. So from pi/2 to 3/4, the GIF of sine of x is 0. For cosine of x, it is -1. So we have two different values now, right? Now, what about tangent of x? Tangent of x takes one of these weird values from -infinity to -1. So there's another possible different value. So we have 3. And then, wait a second. Oh, and then for cotangent of x, it is -1. Okay, I hope you didn't lose track of what it said. So basically, uh, for when x is between pi/2 to 3/4, the GIF of sine of x is 0. So basically, when x is between pi/2 and 3/4, like this, sine of x is equal to 0. Cosine of x, the GIF of cosine of x is -1. And then cotangent of x, -1. And then the GIF of tangent of x is something. But we don't need to worry about that something because we know that it will be different from 0 to 0 and -1. So that means there will be 3 different values. Now, I could go on and keep explaining how to find how many different values there are, but I'm going to leave it to the viewers as an exercise to verify that from pi over 2 to 2 pi, these values, as in there will be at most two values that are equal. And because of that, the cardinality of this set, when x takes values between pi over 2 to 2 pi, is always going to be 3. And also, notice that here we don't need to worry about singular values. They're not singular values. I mean, like, uh, we don't worry too much about this kind of thing where the graph or the function takes a value at exactly 1 point, and then it goes back to 0 at the starting points. Because we're talking about continuous integrals here, so it doesn't really matter if the function is discontinuous at 1 point or just really uh, finitely many points. Well, yeah, I'm doing integrals like an engineer, really. I don't really care that much about the the properties. So that means this actually simplifies to something like this. I'm going to call this function uh, f of x. So this is 2, no, 2 pi. So integral of f of x dx from 0 to 2 pi. This is the integral from 0 to pi over 2 of f of x plus the integral from pi over 2 to 2 pi f of x. So that means f of x here takes the value of f of x between 0 and pi over 2 is 2 between, sorry, here. And then from pi over 2 to 2 pi, f of x is equal to 3. So it reduces to a very simple integral. It's just the process of arriving at this very simple integrand that is quite confusing. E times this is 3 pi over 2. So pi times 9 pi over 2, and this is equal to 11 pi over 2. Okay, do you get it? Let us know. Let me know in the comment section below. So yeah, I think that's all the time we have today. So yeah, goodbye and see you in the next video. Bye.